Right now, as you're watching this, thousands of servers are working together to deliver your video. But here's the thing. Your device only sent one request. So how did it reach the right server out of thousands? Every second, companies like Google handle over 100,000 search queries. Netflix streams to 200 million users simultaneously. Amazon processes tens of thousands of orders per minute. A single server couldn't possibly handle this. It would melt. So what sits between you and all those servers, quietly directing traffic, preventing overload, and keeping everything running? The answer is a load balancer. And it's one of the most important pieces of infrastructure you've never thought about. In this video, we're going to pull back the curtain and see exactly how load balancers work, from the simple algorithms to the clever tricks that make the modern internet possible. Let's start with the simplest setup, one server handling all incoming requests. When traffic is low, this works perfectly. Requests come in, responses go out, everyone's happy. But what happens when traffic spikes? Maybe your app went viral, or it's Black Friday, or everyone's trying to book the same concert tickets. Suddenly, that single server is drowning. Response times climb from milliseconds to seconds. Then users start seeing 503 errors. Service unavailable. Your server has hit its limit. The obvious fix might seem like getting a bigger server. More CPU, more RAM. This is called vertical scaling. But there's a ceiling. Even the most powerful server in the world has limits. The smarter approach is horizontal scaling. Instead of one giant server, use many smaller ones. But now you have a new problem. How do clients know which server to talk to? You need something in the middle to direct traffic. You need a load balancer. A load balancer is a system that sits between clients and a pool of backend servers. Every request from a client hits the load balancer first, and the load balancer decides which server should handle it. Think of it like a traffic controller at a busy intersection. Cars arrive, and the controller directs each one down a different road to prevent any single road from getting jammed. A load balancer has three core responsibilities. First, traffic distribution. It spreads incoming requests across servers so no single server gets overwhelmed. Second, health monitoring. It continuously checks whether each server is alive and responding. Third, failover handling. If a server goes down, the load balancer automatically stops sending traffic to it and reroutes to healthy servers. From the client's perspective, they're talking to a single address. They have no idea there are multiple servers behind it. The load balancer makes a fleet of servers look like one reliable service. Let's look at the simplest load balancing algorithm, round robin. It works exactly like dealing cards at a table. Say you have three servers, A, B, and C. The first request goes to server A, the second goes to B, the third goes to C, the fourth goes back to A, and the cycle continues. It's simple, predictable, and fair. Round robin works great when two conditions are met. All your servers are equally powerful, and all requests cost roughly the same to process. Under these conditions, each server gets an equal share of the work and stays evenly loaded. But in the real world, things aren't always equal. Some servers might be more powerful than others. Some requests might take 10 milliseconds while others take 10 seconds. Round robin doesn't care. It just keeps dealing in order, regardless of how much work each server already has. So we need something smarter, and that's where weighted algorithms come in. Weighted round robin is the natural evolution. Instead of treating all servers equally, you assign each one a weight based on its capacity. A powerful server with weight 3 gets 3 times as many requests as a smaller server with weight 1. So if you have server A with weight 3 and server B with weight 1, the pattern becomes A, B, then repeat. The more powerful server handles a proportionally larger share. This is a simple way to account for different hardware. But even weighted round robin has a blind spot. It doesn't know what's actually happening on each server right now. That's where least connections comes in. With least connections, the load balancer tracks how many active connections each server currently has. When a new request arrives, it goes to the server with the fewest active connections. This adapts in real time. If one server is handling slow database queries, it naturally receives fewer new requests until it frees up. So far, every algorithm we've seen has a problem. A client might hit server A on one request and server B on the next. For stateless services, that's fine. But what if the server stores session data? Picture this. You add items to a shopping cart, and that cart is stored on server A. Your next request gets routed to server B suddenly, your cart is empty. That's a terrible user experience. IP hash solves this. It takes the client's IP address and runs it through a hash function. The hash output maps to a specific server. And because the same IP always produces the same hash, the same client always reaches the same server. This is called a sticky session. The hash function is deterministic. Feed it the same input, get the same output every time. So client 192.168.1.1 always goes to server B, client 10.0.0.5 always goes to server C. The mapping is consistent and reliable. Load balancers don't all work the same way. The biggest distinction is which layer of the network stack they operate at. A Layer 4 load balancer works at the transport layer. It sees TCP and UDP packets. It can read source and destination IP addresses and port numbers, but it never opens the packet to look at the actual content. It's fast because it does minimal processing. Think of it as sorting mail by the address on the envelope without ever opening it. A Layer 7 load balancer works at the application layer. It actually reads the HTTP request. It can see the URL path, the headers, cookies, even the request body. This means it can make intelligent routing decisions. For example, a Layer 7 load balancer can send all requests to /API to your API servers and all requests to /images to your CDN servers. It can route based on cookies, authenticate users, or even modify the request before forwarding it. Layer 7 is slower but far more powerful. No server runs forever without issues. Hardware fails, software crashes, networks glitch. A good load balancer doesn't just distribute traffic, it also makes sure it's only sending traffic to servers that are actually working. Health checks are periodic probes that the load balancer sends to each server. The simplest form is a TCP ping. Can I connect to this server? A more thorough check is an HTTP request to a health endpoint. The server responds with a 200 OK if it's healthy. If a server fails a certain number of consecutive health checks, the load balancer marks it as unhealthy and removes it from the pool. Traffic is seamlessly rerouted to the remaining healthy servers. The client never notices. When the failed server recovers and starts passing health checks again, the load balancer automatically adds it back to the pool. This entire cycle is automatic. No human intervention needed. It's what makes modern services feel reliable, even when individual servers are constantly failing behind the scenes. Let's connect the theory to real tools that engineers use every day. nginx is one of the most popular software load balancers. Originally built as a web server, it also excels at Layer 7 load balancing. A simple upstream block in nginx config lets you define a pool of servers and choose an algorithm. nginx is free, open source, and runs on standard hardware. HAProxy is another heavyweight. It's purpose-built for load balancing and supports both Layer 4 and Layer 7. HAProxy is known for extremely high performance and is used by companies like GitHub, Reddit, and Stack Overflow. In the cloud, providers offer managed load balancers. Oz has the network load balancer for Layer 4 and the application load balancer for Layer 7. Google Cloud and Azure have similar offerings. These managed services handle scaling, health checks, and failover automatically. Most production architectures use multiple layers. A cloud load balancer at the edge, distributing to application servers running nginx or HAProxy internally. Let's bring everything together. We started with a single server that couldn't keep up. The solution was horizontal scaling, using multiple servers behind a load balancer. We explored the algorithms, Round-robin deals requests in order. Weighted round-robin accounts for different server capacities. Least connections adapts in real time. IP hash provides sticky sessions for stateful applications. We discovered that load balancers work at different layers. Layer 4 is fast and simple, routing by IP and port. Layer 7 is intelligent, routing by URL, headers, and cookies. We saw how health checks automatically detect failures and reroute traffic. No downtime, no manual intervention. And we connected it all to real tools. nginx, HAProxy, and cloud load balancers like AWS ELB. Every time you stream a video, search the web, or check your social media, load balancers are silently working behind the scenes, making sure your request reaches the right server. They're the unsung heroes of the internet.